everyone! So today we will do another AMC problem, and it is problem 21 from the 2016 AMC 12B, and it goes as follows. So we have a unit square ABCD, and the midpoint of side CD is Q1. And then for I being 1 to infinity, we'll let PI be the intersection of AQI and BD, both segments, and we'll let QI be the foot of the perpendicular from PI to CD, and we want to evaluate this infinite series right there. So first, it might be a good idea to start well with a little drawing. So that is exactly what we will do. So we'll have a square that's straight probably. So we have a square with side length 1, if this even is a square, ABCD, and then we draw our diagonal BD because it will be used a lot of times. There we go. And then Q1 is the middle of CD, and then P1 will be the intersection of AQ1 and BD, so that's P1, and then drop the perpendicular and the foot will be Q2. Q2 sounds like a Japanese restaurant for some reason. Okay, never mind. So, and then we connect A and our Japanese sushi brand, Q2, to get P2, and then drop the perpendicular to get Q3, and this goes on until infinity, and we want to sum up all of the areas of dPi/QI where I runs from 1 to infinity. Okay, so how do we proceed? Well, first we will let PK have coordinate. Wait, actually, first I'm going over base. We'll place a coordinate system centered at D, which will be our origin. So this is the y-axis, x-axis, and then this means that C will be 1, 0, B will be 1, 1, A will be 0, 1, and D will be 0, 0. Okay, and now line BD will have the equation y equals x, obviously, and then we will let PK, well, our points have coordinates xk, comma, and the y coordinate will also be xk since they all lie on BD, which means they all lie on the line y equals x, which means their coordinates will be equal. And then this means that the coordinates of QK will be, okay, so they will be xk minus 1, 0. The y coordinate is 0 because they all lie on CD, which lies on the x-axis, and it will be xk minus 1 because here we have Q2 has coordinates x1, 0 to 1. And then this implies that if we let k be equal to 1, we have Q1 has coordinates x naught, 0, but since it is the midpoint of CD, it has coordinates 1/2, 0, which means that x naught equals 1/2, and this is a very important initial condition. And now what we want to do is we want to find a recursive formula for xk, and here's how we're going to do this. Should I choose color? Yeah, no, let's use the same color. And there's someone going down the stairs, I believe. Okay, so now we know that PK, by definition, is the intersection of segments AQK and BD. I thought the comma was a 1, but it's not. Okay, so the equation of the line BD is simply y equals x. And the equation of the line AQK will be y is equal to, okay, so the slope will be 1 minus 0 over 0 minus xk, so negative 1 over xk times x plus 1 because that is the y-intercept. And now, to find the intersection point, we can set those equal to each other, so we get x equals equals negative 1 over xkx plus 1. But then that x will actually be our xk plus 1. That will be the next step in our iterative process, because we have xk and then it intersects to get xk plus 1, xk plus 2, so on, so on, so on. And now we just solve for xk plus 1. So add this term to both sides, we get xk plus 1 times 1 plus 1 over xk is equal to 1, which means xk plus 1 is equal to 1 over 1 plus 1 over xk. Good. And now we have our recursive formulas, but when dealing with summations, it's much easier to have an explicit formula. So we'll find such a formula. So we know that by definition, x naught is equal to 1/2. And then x1, if we plug it in, we get 1 over 1 plus 2, which is 1/3. Plug that in, we get 1 over 1 plus 2, 3, which is 1/4. Plug it in again, we get x3 is equal to 1/5. So on, so on, so on, up until infinity. And from all of this magnificent sequence, we can claim the following. We can claim that xk is equal to 1 over k plus 2 for k greater than or equal to 0. And now, to be sure of this, we'll prove this claim by induction. So for our proof, I don't know if I'll have the space. I will have the space, because I have to have the space. Okay, so our proof will let P of k be the statement, well, our statement xk equals 1 over k plus 2. So for our base case, we have P of 0. Well, that's our first case, so that's our base case. And if we plug in 0, we get x naught is equal to 1 over 0 plus 2, which is 1/2, which is obviously equal to 1/2. Obviously, that's really trivial. 1/2 is equal to 1/2. Okay, now I don't have the space, so I'll continue the proof. Where should I continue the proof? I'll continue it right there. So, yeah. And okay, so, yeah. Now that our base case is proved, for our inductive step, I write so well, my calligraphy is awesome. I have the potential to become a doctor. Okay, so we'll assume that there exists some n out of v positive integers such that xn equals 1 over n plus 2. Well, that is our Pn. And now we'll consider P of n plus 1. So we have xn plus 1 is equal to 1, is equal to 1 over 1 plus 1 over xn, which is by definition, since we assume 1 over n plus 2, so we'll have 1 plus n plus 2, which is n plus 3, which can be broken up as n plus 1 plus 2, which respects our claim, our formula for xk, which means it holds by mathematical induction, which means this formula is true, and the 2 just got sliced in half. Okay, so we now have our xk, and our next step is to use this formula to find the area of dpk xk in terms of k, and then plug it into this infinite series and evaluate the sum from there. But first I will clean up this board, because if I can fit a proof for induction, I certainly can fit in an infinite series on my board. Okay, so now that we've cleaned up this board, we can finally continue our problem. Okay, so far we have this explicit formula, and then we'll let AK be the area of the polygon DPK 2k. Yeah, that's right. New k, 2k. Okay. In other words, our summand. And now we'll draw ourselves a sample triangle. So first vertex is D with coordinates 0, 0, in other words, the origin. Second vertex is our PK with coordinates xk, xk. And last is our QK with coordinates xk minus 1, 0. And now DQ will be xk minus 1, and the height of our triangle will just be xk since that's the y coordinate of x, which means AK is, well, we know that the area of a triangle is nothing but 1/2 base times height, one of the many formulas that were drilled in our heads in middle school or whatever you call it in the US. Here is secondary, never mind. So 1/2 xk minus 1, but then xk is 1 over k plus 2, and xk minus 1 is 1 over k plus 1, so we have 1 over 2 times k plus 1 times k plus 2. Yeah, that should be right. Therefore, our infinite series, the sum as k goes from 1 to infinity of the area of triangle, not a triangle, dpkqk is equal to, well, it's equal to, plug this in, factorial the 1/2, the sum as k goes from 1 to infinity of 1 over k plus 1 times k plus 2. And then we have 1/2 sum as k goes from 1. Actually, we'll rewrite this infinite series. We'll re-index it so that it starts at 2. So we'll have the sum as k goes from 2 to infinity of 1 over k times k plus 1. It will make things nicer like this. And now, this can be simplified using partial fractions decomposition, but I will skip this test because it's really trivial, and this is left as an exercise to the viewer. So, we're left with 1/2 sum k goes from 2 to infinity of 1 over k minus 1 over k plus 1. And now this is just a classic example of a telescoping series. So we have 1/2, we can write it as 1/2 times the limit as sum n goes to infinity of the sum as k goes from 2 to n of 1 over k minus 1 over k plus 1. In other words, we're taking a look at the partial sums, and my writing just goes like up, and it will go down soon, I guess. So have 1/2 limit n goes to infinity of, okay, so expand this series, so we get 1/2 minus 1/3 plus 1/3 minus 1/4 plus so on plus 1 over n minus 1 over n plus 1. And the beauty about a telescoping series is that things cancel, namely 1/3 will die, 1/4 will die, everything there up until 1 over n will die. As n goes to infinity, this term will go to 0, in other words, will die, and we're left with 1/2 times 1/2, which is simply 1/4. So yeah, this was a pretty nice problem. For me, it looked intimidating the first time I read it, but then I went through it, and finally it wasn't that important to do. So yeah, it was a nice little problem. So this is a video. Thank you guys for watching. If I really did get actually, it's just all you know, it's just this video. Bye.